Howdy hackers, and welcome to another episode of FairLight TV. You also just saw my Christmas present to myself, a FairLight TV t-shirt inspired by the intro, the legendary intro episode we just had. Okay, so normally the episodes we are producing are sort of deep diving into the technology of C64 and to some extent also Amiga. This time the idea is to dive into something which is sort of more shallow, more like a beginner's guide to machine code programming. So bringing more people on board with a technical understanding, so eventually you can go back and dig into the more deeper episode. I hope you will like this one, so stay tuned and see what happens now. Computer runs programs in machine code, and when you code, you write code directly into machine code, which is a very cumbersome way of doing it. You compile something into machine code, and there you use like an assembler or C code for that matter, like a higher level programming language that still compiles into machine code, and C would be an example of that. Or you can compile to some kind of pseudocode that runs into a virtual machine, and I would say Java is an example of that. Or you can have like an interpreter that reads the programming code in like humanly readable format and executes based on that. And there you would have PHP and JavaScript and such programming languages that would apply for that last category. Here we will concentrate on coding machine code, and the same principle sort of applies to all platforms. So if you are interested in the C64 or Amiga or PC for that matter, coding machine code is kind of in principle the same. You need to understand a lot about the processor, and you need to understand about the environment you're coding for. But if you know machine code on one platform, you have sort of a principal advantage of learning machine code on another platform as well. So let's dive into machine code programming. Okay, so what you need to do first is, of course, establishing some sort of development environment, because learning this, the trade of coding machine code or any sort of coding, I would strongly encourage you to apply some sort of learning by doing kind of approach to it. So when you study it, you test it and see that you actually understand it by actually seeing it work in practice. The Transmission 64 episode we just had went through setting up a development environment on the C64, but this is not like system dependent. So if you are into Amiga, you might be interested in picking up one of the native assemblers that run on the native platforms. That would be DevPack, ASM1, or PHXAS as the three recommended one. I'm not a very skilled Amiga coder myself, so these are assemblers suggested to me. And they run on the actual Amiga. And since if you have been watching the Transmission 64 episode, where I strongly discourage anyone from running C64 assembler on the actual C64, it's a lot easier to run Amiga assembler on the actual Amiga, because it's more, given that it's multitasking environment, allows you to do a lot more with the same memory and all of that. So but there is of course always the opportunity of running something like VASM and then test the result in a cross or in one of the emulators like Win UAE. But let's go into the gory details of starting to understand coding machine code for the C64 and Amiga. Okay, I'm truly sorry if this is sort of a boring start, but in order to bring everybody up to speed, I need to start from kind of the base level here, and that is counting. Us humans, we tend to work with the decimal system, and decimal is probably, so it's a base 10, and the assumption here is that because we have 10 fingers, that is sort of a natural thing to us. But we need to be able to extend a bit beyond that to understand machine code programming and understanding computers in general. So, but decimal means that we have a base 10 and we have 10 symbols to help us count. And the symbols are 0 to 9, so 1, 2, 3, 4, 5, 6, 7, 8, 9, and then the 0. And when we run out of numbers or sort of dedicated symbols, we also have a way to express something which is bigger than 10. And then we use positioning, and we put 2 symbols there, and the position of them is relevant for the number we are trying to express. And this sounds stupid, but it's key to understand that we are doing this in order to take the step to the next, to the other bases here. So the position, the position here is telling us more than the symbols themselves do. So if we take 9 plus 1, that turns into 1, 0. We call that 10. And here we have a 0 in the column for ones, and then we have a 1 in the column for tens. From a more technical perspective, it's the rightmost position is base to the power of 0, and the second column is base to the power of 1, and the third is base to the power of 2. So that is sort of what it is. So if we take the number 1, 2, 3, we have 3 to the power, which is times 1. And then we have 2 times 20, and then we have 1 times 100. That gives you the number 1, 2, 3. It's quite easy to see it if it's decimal, and again, decimal is very convenient for us humans. But when we look at computers, they run into binary code, and they only have 2 symbols, zeros and 1. And that is, so binary is base 2. And if we take the same logic here, the rightmost position is base to the power of 0, so that's 1. And here the base, again, is 2, right? Second is base to the power of 1, and that is 2. Third is the base to the power of 2, which is 4. So if you take the number, and I here express it with a percentage sign, preceding percentage sign, which is a common way to indicate that you are actually referencing binary. So 101 is 1 times 1, 0 times 2, and 1 times 4. And that means 5 in decimal. Yeah, if you want to express it in decimal. If you look at, I've just here listed the first 3 columns, but it's quite convenient to understand the full series here, because there are, for many purposes, that's rather convenient of you to know. So it's 1, 2, 4, 8, 16, 32, 64, 128, 256. Okay, so that's sort of the first 8, right? 9. And then 512, 1024, 2048, 4096, 8192, 16382, 32768, and then 65,536. So that's binary, and if you want to express a rather large number, anything like beyond like a few thousand, the number of characters you need to express that number is quite difficult to manage from a human perspective. We are better at handling a little bit more complex symbols, more symbols, and then less length. And that is sort of a key argument to find something which expresses binary in a way which is more convenient for us humans. And this is why we tend to use hexadecimal. And let's go into hexadecimal here. So here we have more symbols. So we still use the same 0 to 9, and then we also use A to F. So that makes up 16 discretely different symbols. And you are aware of them. We don't need to learn any strange symbols that are new to us, because you already know A to F and you know the logical order of them. And the only thing you need to learn here is that you start from 0 up to 9, and then the alphabet symbols come afterwards. So that is base 16. And if we apply the same logic that we learned from decimal and binary here, the rightmost position is base 16 to the power of 0, again 1. And the second one is base to the power of 1, and in this case this is 16. And the third one is base to the power of 2, which is 256, which is 16 times 16. So if we take an example here, and here I use the $sign, which is a common way to denote that you are referencing a hexadecimal number. One of the other ways is a 0x. That's also common for denoting that it's hexadecimal. So 1, 2, 3, hexadecimal 1, 2, 3. That is 3 times 1, 2 times 16, and 1 times 256. So the 1, again, the rightmost position, the 2 in the middle position, and then the 1 in the rightmost position here. That means that it's 3 times 1, 2 times 16, and 1 times 256. And that turns into be 291. If you're using Windows or anything else, I'm sure you have a calculator there. There is called a programmer's calculator, which will help you convert between the bases in a very easy way. But the reason for hexadecimal here is that computers work in binary, but not only that, they group binary by groups of 8, and we call them bytes. And then you have words and long words and what have you not. But let's just focus on the 8 bits first. The good thing here is if you split that byte into 2 4-bit segments, we tend to call them nibbles. Every nibble can be between 0 and 15, or between 0 and F, because there are 16 possible combinations that a nibble can hold, which means that you can express one of those 8-bit bytes with only 2 hexadecimal numbers. So it is convenient, and that is the reason why hexadecimal is a convenient trade-off between humanly understandable, but also correlating directly to the binary underneath. Because if you have the hexadecimal number, then converting into binary will be rather easy, because you know that every character is translatable directly to 4 bits. So that is counting when you are a low-level programmer, and you need to learn this. If this was complex, go back, see if you can understand it by listening to it again, if you didn't catch it the first time around. Or if you simply didn't understand, then feel free to Google around and see if anybody is managing to kind of reach you by explaining it in another way. Because you need to understand hexadecimal if you want to code assembler. You really have to. So let's move on to the next part. Okay, so let's go into the core here. The core is the central processor unit, or the CPU, or the processor. You can call it whatever you like. The processor is the unit inside the machine that does all the work, and they have become immensely difficult to understand. But let's focus on the ones that we have at hand, and they would be the 6502 and the Motorola 68000. So the MOS 6502 is the one that sits in the Commodore 64. It sits also in other machines, whereas where I think Apple II is one of them, Atari 800 and 400 and 800 XL. A number of the MSX machines were also 6502 based. Basically, the competing processor for low-end system would be the Z80. Commodore bought MOS, and they made a special version of the 6502 called the 6510. It's sort of pin compatible to the 6502, but the 6510 has some sort of memory management function as well. I think you can take a 6510 and put that in any other machine, and that will work unless you start fiddling with address 0 and address 1. But if you take a 6502 and put in the Commodore 64, that wouldn't work, because the C64 relies heavily on the special features that is implemented in the 6510 over the 6502. The Amiga uses a Motorola processor called, or a processor family, I would say, that's called 68000. So that one was developed, so there was a 68010, 20, 30, 40, 50, and 60. They became faster and they had more instruction and all of that. But even the first one was a CISC, a complex instruction set computing type of processor. Those processors are where each instruction is very competent and can do a lot of things, and can span over multiple cycles. Whereas RISC processors, they have more simplified instructions, so you might need to combine more of them to make sort of the same thing as a CISC instruction can do. But on the other hand, it's easier to scale the processor. The processor becomes simpler, and you can start kind of boosting the actual clock speed. So there are trades of RISC and CISC. I have no idea if 6502 is a RISC processor or a CISC processor. At the time, I think you would say it was a CISC processor, but given how time has evolved, I'm sure by now it's sort of a RISC processor. So what a processor can do is basically loading values, manipulating values, and storing values. 3 things it can do. That's everything you basically need to know. And then it has addressing mode, so it can read from this based on index, based on relative indexing or absolute indexing, and all of that. But the 3 basic things is still loading, manipulating, and storing it back. So the computer has memory, and that is sort of where all of the things happen. But there is also additional memory that the computer can, or that the CPU can use for its own purposes. There is a program counter that keeps track on where the program, the next instruction that the CPU is going to execute is placed. So that's a reference in memory. There is also a status flag register where it stores statuses of previous instructions. So if you do a comparison and what you compare is equal, then there is an equal flag that you can use to branch based on the comparison. It uses the equal flag in the status register for that. The Amiga has a lot of internal register. It has 8 address registers, and it also has 8 data registers. That's plenty if you look at the C64, because the C64 has an accumulator. So everything that the C64 does, or the 6502 does, is going basically through the accumulator. All subtract, all add, all load, all stores, not all of them, but the predominant majority of them are using the accumulator. So one single data register for that. And in addition, it has X and Y. So these are two registers used for indexing, where you would load from this address with the index in X. That's one of the addressing mode that you can use for that. So that's why X and Y are handy as well. But the Amiga is, of course, a million times more competent what you can do in terms of addressing modes using the address and data registers it has. So instructions, they affect the flag. And the cool thing with that is, let's say you do a subtract. You have 5 and you subtract it with 5. That means that the result is 0. Then the CPU already knows that after doing the subtract that the result was 0 and set the 0. You basically never need to compare with 0 to ensure that you set the flag, because you already have the flag set from the subtract. I get totally annoyed when I see compare with 0. That's so wasted. You shouldn't do that. You really shouldn't do that. Okay, and then there is also a temporary area that the CPU uses, which is called stack. It's a temporary area, and the logical structure used is stack. There are two kind of structures that is thinkable of using for the computer. One is a stack, and think of it like a stack of plates. If you wash one of the plates and you put it on the stack, if somebody picks up a plate, it will pick up the one on the top. So the first one you placed is the first one picked. It's first in, first out, FIFO. The alternative is a queue where you place something but the first item you pick is from the bottom or from the other side. So that is LIFO, last in, first out. So the C64, there are a number of hard-coded things in the processor. First of all, a number of the addressing modes are handling parts of the memory a bit different. So the lowest page of a memory, and a page would be all the 256 addresses that has the same first eight addresses. So if the address starts with a 00, that will be on 0 page. So page 0 or 0 page. The first page or page 1, where the address would be 01 and then any number, that is where the CPU has hard-coded stack. So the C64 processor has a 1 byte long pointer that points to the stack. It doesn't point to the actual address. You cannot relocate the stack. It's hard-coded to be on page 1, or where the page is 1. So that was sort of everything when it comes to talking about CPUs and how they work from a very kind of topology kind of perspective. And again, I would like to highlight that the CPU in a number of machines are the same, so you can study a book about the CPU without any sort of understanding of the environment that the processor is supposed to be run in. So you could actually run like a machine code programming book for the Atari, even if you're intending to use it for the C64. You just need to disregard the specifics when they talk about Atari, because the processor is the same. My personal favorite book for the 6502 is this one, and I have been rather bad because I've put a sticker on top of Programming 6502 by Rodney Zacks. I was sort of heavy with stickers. this one looks in pristine condition, and it sort of is, because I had this in English first, and that one I have somewhere, and that one has pink marking all over it. I read that one, and then I just bought a Swedish one, which I basically haven't read. I just put stickers on it. So this is first it goes through the processor and educate you very, very well on programming it, and then the other portion is sort of a reference to what the instructions are doing and the schematics of how the instruction work and what flags it sets and what addressing modes each of the instruction is compatible with. Let's do roll here. So that rotate left shows you the rotation address, or the rotation mechanisms, and all the these are the addressing modes here, and these are the flags that the instructions are setting when it's executing. So programming the 6502, this one is available in English. This happens to be a Swedish copy, but please disregard that. Another Swedish copy is Programming the 68,000 by Steve Williams. So this is the book I read about the 68,000. I can't say I'm much of a 68,000 coder, but so it contains the basics of programming and the same sort of reference that you saw for the 6502, but this is for 68,000 instead. The addressing modes and what happens, and a bit of text. Here you would have the flags it sets. So the N isn't affected. The Z is set if the tested bit is 0, otherwise it's zeroed. C and V aren't affected. So pretty much the same as you would find in the 6502 book, but this one is for 68,000. You could have, and these are more sort of, you can read them as books, and parts of them are like educational books, but parts of them are more reference books. I could point out this one as well. It's First Steps in Assembly Language for the 68,000 by Robert Erskine. This is more like an educational book if you want to learn how to code 68,000. It's not working as a reference. It's more like a book, like a study book if you want to learn it. So that might be a good thing, but I would recommend you to also have some sort of reference book. Okay. Yes, I think that was everything I wanted to say about the CPU and addressing methods and all of that. Again, we will not go into the details of programming on any particular platform. This is sort of only highlighting a number of items where you would need to kind of dig on your own afterwards. So now we will look at reference books for the respective platforms. So platform books. Okay, so that was learning to count and learning about the CPUs. References about the CPU and programming practices around the CPU. But in order to actually use it, you need to understand how you should program the respective system. So you need some sort of reference book in order to understand what to kind of manipulate in order to have the machine do what you want. For the C64, this is probably a book I've shown before. The Commodore 64 Whole Memory Guide by Melbourne Books, I believe. Tim Arnott's book. This is the one I use myself. I simply love this book. Again, it's not something you can like read. You can browse through it, but it's predominantly a reference. It references all the I/O. So when the system is running, you have 0 page, and the system stores a number of values on the 0 page, and all of them are explained. It stores a number of values on the page 2 and page 3 as well, and they are all explained. And then the different values that you can poke into the respective registers of the I/O chip. So the VIC chip for graphics, the SID chip for music, and the two CIA chips. It's all in here. And then there is also, let's see if we can see that. So that is a complete disassembly, commented disassembly of the C64 kernel and the C64 basic ROM. So a very comprehensive book, and again, sorry for my little notes here that disappear anyway using the green screen effect. I have little tabs because this is something I use a lot. So I love this one. I know most friends I have tends to use Sheldon Lehman's Mapping the Commodore 64. I do have that one, I just didn't find it when recording this one. So what I have here is Mapping the Commodore 128. This one is not by Sheldon Lehman, it's by Otis Cooper. Okay, yeah, so this is the book. A lot thicker than the Mapping the C64. This one is doing basically the same. It's explaining everything. It doesn't contain any disassembly of the ROMs. It's thick as it is, so you can use it as a reference book, but it has more text than like a regular reference book. There is a lot of educational stuff, but you basically need to look up the portions you want to kind of dive deeper into and read more about it, because a number of like the SID registers and stuff, they are spanning several pages in this one. I don't have any examples of the Amiga books here, but back in my very early Amiga days, first of all, the book to get is the hardware reference manual. That is sort of the Bible for anybody coding demos on the Amiga. So that is like all the hardware I/O registers for creating, for accessing all the hardware registers on the machine. But that is sort of assuming that you want to take over the entire machine and have a demo that kind of takes over the entire machine. If you want to do anything that is sort of system friendly, you need to educate yourself as well on how to program on the Amiga system. And there you have the series of Amiga ROM kernel reference manuals. There is libraries, devices. Originally, libraries and devices was one book, but since the libraries and devices developed, I think that sort of split into two books. So if you want something which is sort of the recent releases of Amiga-DOS, you want the versions with the separated libraries and devices. Again, my understanding, and I'm not really an Amiga coder. There is one for exec, there is one for includes and autodocs as well. So these are sort of the, I don't know, what would that be? 1, 2, 3, or possibly 4 books plus the hardware reference manual. So these are sort of the reference books you want to have when you want to code for the Amiga. There is also like some sort of style guides on how to code Amiga applications that sort of conform with the visual language that you are supposed to conform to when you code on the Amiga, if you care about that. Again, these are reference books. So if you want to code, you need to understand the CPU, and then you also need to understand the platform. And the latter section has been about understanding the platform. Beyond this, you can find a lot of programming books. There is like the C64, the graphics book, that just educate you on graphics programming on the C64. And there are, I'm aware of a number of Amiga gaming programming books, which sort of, that has a totally different angle. That sets the objective. You want to do this. And then the CPU educational part and the system educational part is sort of parts of what you need to kind of go through in the book in order to deliver on the objective of the book. So that's a different angle. No reference whatsoever. That's more something you read through, and then you just follow the logic of how they want to teach you like that. That's one way of learning. If you are better off like that style of kind of educating yourself on something, then those might be for you. But if you want to really build a solid ground, ensuring that you really know your thing, then I would urge you to get books for the CPU, books for the system, and then possibly as a later stage, get a book that would educate you on a specific topic, such as like the C64 graphics programming book or any of those. That was everything I planned to kind of go through today. I hope you have enjoyed this, and please share any link to any book or any other source that you find useful for kind of your understanding of the system. I could reference stuff like GameBase 64. No, sorry, Codebase 64, of course. That is an online sort of a database that goes through a number of relevant programming examples for different topics on the C64. That's one where I tend to copy and paste, especially when writing disk I/O. I tend to copy and paste the examples from there because they are rock solid. So, and I'm sure there are similar sites for the Amiga where you can learn different kind of tricks and tips and tricks for solving specific programming problems on the Amiga. And if you have such examples, please post down below and share those experiences with us. Thanks so much for watching, and see you in the next episode of FairLight TV.